World Spaceflight News Special Report.
So how do we make this stuff? The answer is exactly the way we did before. So this is a photograph of Apollo heat shield manufacture from the late 1960s. And the way this works is you have your carrier structure built, you come in and you adhere an open cell honeycomb matrix down on that structure, and then fill each individual cell of that matrix with the AVCOAT ablative material through what are essentially glorified caulking guns. So this is how Apollo did it. And to get a feel of how we did it, got this little video here. Tim is playing. So we've got the heat shield sitting on a table there in the back, and there's a crew of technicians that stand around it. In this case, we used a crew of 6 technicians, 2 shifts a day, 6 days a week, and it took about 4.5 months to get this done. And you just sit and gun individual cells. You can see the guns they're using there. They take a cartridge full of the material in the back. They're pressurized and heated, which are the wires hanging down. And you just pick out your section, put your earphones on, and go for it. So you can see this is a hand process. You see fingers involved and all that, and that's the way Apollo did it, and that's the way we did it for EFT-1 as well. Let that finish out. So there you go. To kind of give you a sense of the way that this progressed, this is a picture of the EFT-1 heat shield, the flight article, sort of about midway or so through manufacturing. And you can kind of see the 3 different stages here. Because the material has we call it an out time, it's a shelf life. So it expires some number of days after it's actually made. You have to use it by that time and cure it by that time, otherwise it becomes bad. Our heat shield is big enough that we can't do the whole thing in one go with one batch of material, so we do it in sections. So we have, on the top there, you see a picture of unfilled honeycomb. So that's the honeycomb matrix laid down on the carrier structure. The purpler sections are areas that have just been gunned and have not been cured yet. And then the more tan sections have been cured. So you lay down your honeycomb, gun a section, cure. Gun the next section, cure. Gun the next section, cure. And move on like that. And then at the end of the day, there's one final cure at a higher temperature to kind of lock the whole thing together, which will become important in just a minute. So we had some challenges on the EFT-1 build. We had 2 major issues, and as we'll talk about, neither of them were actually new to this system. The first issue we had is the flight heat shield AVCOAT cracked during the final cure. So this is the thing we're supposed to fly in a year, comes out of the oven, and it's got cracks in it. Primarily, those cracks occurred in the seams between those honeycomb sections. So the honeycomb goes down in panels. We don't have one big 5-meter disc of honeycomb. It goes down in panels, so there's seams. And that's where our cracks occurred. The second problem we had is that we started to show analytically that the heat shield, the AVCOAT on the heat shield might crack during the mission, either by getting cold on orbit or due to the stresses of entry itself. This was largely driven by the strengths we were getting from what we call witness panels, which is how we sort of verified workmanship on the flight build. I'm going to dig into those 2 issues here in the next couple of slides. Cracks are not good, right? If you have a crack in your ablator, then you've opened up a pathway for hot entry gases to get down into your structure, which is the very thing that you have the heat shield for in the first place, is not to allow that to happen. So let's talk about the first problem first, manufacturing cracks. So we pulled the heat shield out of the oven for its final cure, and we found 28 cracks in various locations on the heat shield, and you see the map of those cracks there on the lower left. We think those were likely caused by thermal expansion, by stress concentrations at the seams, and I'd also add probably some material quality problems along those seams. And you can get a sense for what they look like. We're not talking about vast canyons here. We're talking about little fractures there on the right, if you can see them at that resolution. Yeah, you can kind of get a feel for it. So, needless to say, there was consternation and gnashing of teeth because of this. But we got through it. How did we do that? Well, we fixed them, right? One of the things that we got by using a system that had been done in Apollo was a whole set of specifications for how to fix problems. So they actually had repairs for this type of issue already spec'd out to use. And we implemented those repairs. Now, because things were a little bit different and because you always check somebody else's work, we went ahead and certified those repairs for our own flight in our own way. The way we did that is you've got on the upper right there what a crack on the heat shield will actually look like. On the lower right, you've got a repair. That same crack has been repaired with these overlapping plugs. On the side, what we did is we built up test articles with the repairs in them, in this case, ArcJet test articles, with overlapping plug repairs. We tested them in the ArcJets, took them out, checked how they worked, checked all the temperature data, and they were all fine. So we certified the repairs for flight as well as the pristine system. So I mentioned that we got some of these spec repairs from Apollo. When this happened, one of the things we did is we actually commissioned different folks around the country to go and photo survey whatever crew modules we could get to in the various museums. And it turns out they're basically all there to go look at and photo survey. So we did that. And these kinds of repairs are on every single Apollo crew module that you can go look at. They're all there, lots of them. So repairs of this nature are a standard part of the honeycomb gunned Avcode system as evidenced by the Apollo capsules. Didn't make us feel better at that time, but it is something worth noting. I'm going to talk a little bit about that too. So the second problem we had was we were actually predicting that the ablator could crack, or we call it negative stress margins, during the EFT-1 flight. But it was impossible to verify whether or not that was true on the full flight article, right? If you think about a 5-meter heat shield sitting there that you've basically built in situ or in place, put your honeycomb down, gunned it, and it's done. We don't have a way to test that, to bend it, pull on it, heat it up, cool it down in the same way that we expect to happen during the flight itself. So we have to rely on side methods or coupon bench level tests to do that. The way we did this on the flight build is we used something called a witness panel. A witness panel is a panel that sits off on the side. You can see it here on the left in the green circle. Where am I lost it? There it is. The green circle here on the left. So you'd have the technicians gunning the ablator into the heat shield. After some time, they'd turn and gun some into the witness panel. Then they'd turn back to the heat shield, then back to the witness panel, back to the heat shield. And so the idea is that this witness panel on the side is representative of what's being done on the flight article. So we take that witness panel, cure it, cut it up, and start testing it. We did pull tests like you see in the upper right there, tension tests. Measure the strength, measure the density, et cetera. And the thing that happened is all of that data was coming back with lower strength primarily and density than what we expected or what was even required. The plot in the lower right is showing the region that would be good or in spec is sort of this middle upper square here. And then I plotted the data points from those witness panels. You can see there's a large portion that are out of that box. So when you go and fold those kind of results into the flight predictions into the predictions for the flight test, that's where we started seeing the negative margins come up. So they're left the hanging questions, well, are these witness panels faithful witnesses, right? Are they actually what's on there? But that's what we had to deal with. That's what we had to work with.